Hi guys, welcome to my seminar today, which is about model pruning, a technique to reduce size of the models but still maintain the performance and the accuracies. So let me introduce something about model pruning. So why we need model pruning? The reasons is today's AI is too big. Here's a graph about uh, model size, and here is just really a small model in compared to some large language model today, which includes about billions trillion parameter. So in conclusions, AI is too big now. So the gap between the model size and GPU memory is quite large. Like with the GPT-3 model, it's nearly 200 billion parameters, whereas a really big GPU, really expensive GPU, such as a 100, it does have 80 gigabyte GPU RAM, GPU memories. So we need some technique to uh, break the gap between the model size and the GPU memories. The techniques like pruning, quantization, something else. And today I will bring you one of these techniques, which is model pruning. Pruning it also happens in human brain. You can see in this picture here, when we were born, lies um, a model from scratch with random parameter, and we learn as the model will be trained, and then the number of neuron increase when we grow, and then by the time it decrease, uh, lies in these pictures. And model prunings also based on that ideas. Here is a picture about model neural network pruning. Like it's a process to make neural network smaller by removing some synapses and neurons, like remove the redundant neuron on human brain. So here is pictures indicate that model pruning shows some really good result, like when we uh, prune about 90%, the performance of model still really good. Let's move on some results that were tested on some datasets. Like when we prune 90% of our models, we still receive a really good results on the capture image capturing task. You can see here. So in conclusion, about the pruning, it's just a process to make neural network smaller by removing some redundant neuron. So let's move on to how to uh, remove their neurons, and what is the criteria, the pruning ratio when pruning a model. First is fine grain or untrusted pruning. You can see here a matrix, and we just randomly choose the neuron, the cell to prune, and all the prunes will have the value 0. But it really random and hard to accelerate. Like we still maintain the size of the matrix. However, a really is a really nice approach. Let's move on to another approach, a higher level approach, like structure pruning. It can be the vector or matrix level. not a random or cell level like the left one. Let's look at the right one. We can see here. Uh, it's a less flexible pruning technique because it's not random. It's like a vector level here, and we choose some vector to prune. Then the overall size of the matrix will reduce, like the image on the right. Here is uh, some case when you pruning. The first one is fine grain, like random pruning. We can also use some pattern pruning, like the second one from the left, or more structure like vector, kernel, and channel. And from left to right, the um, from the left to right, the flexible is reduced, but it support more on accelerator and reduce the size of the model and also support the parallel computing. Um, Here is um, some statistics about model after pruning, like AlexNet. We can prune um, over 90% to reduce from 61 million parameter to just about 6.7 million parameter. So let's move on about how to select neuron to pruning. Let's look at a neuron, and we really familiar with this image, like when we have a function and we pass it to activate activation function. Here I use relu, and after the relu function, we can receive result, and uh, it will be the same before pass to the relu function if it's greater than zero, else it will equal to zero. So we can see after go to the relu function, there are a loss of parameter will become zero. So how here we can see a really much r- redundant parameter need to remove. So here is an example how you can remove the redundant parameter. We can base on the absolute error, and let see a metric here. With this metric, what is the uh, neural, what is the cell we can prune? You can calculate um, the absolute errors, and um, let's choose a prune ratio um, is 50%. Then let's keep the 3 and minus -5 and prune 1 and -2. Another approach is in a vector level. You can see here. We can calculate the L1 norm by row by rows, and thus keep the row which has uh, the bigger L1 norm, and um, remove the row with smaller ones. You can also use some technique like L2 norm as well as uh, LP norm. Here, in this example, P is equal to 2, so you can see the same picture in two slides, but you can imagine that if it's a 2 by 3 matrix, so it can be three parameter, and it will be uh, a, yeah, um, another another thing here. With the channel level, we can also uh, let's see in the picture. We can also prune uh, by channel levels. Here we have, and we can based on scaling factor. Scaling factor is a trainable parameter which will multiply with the output of the filter after convolution. And here we can see some scaling factor, and we will keep the filter which have the bigger scaling factor ones and remove the smaller to get a smaller um, size here on the right. Also, pruning is also one of the objectives when pruning is that we reduce the size of the model but keep the accuracy, keep the metric will be maintained good. So we can also approach that as the minimize the loss between model before the pruning and us and model after pruning. Is also a way to approach how to pruning a model. Uh, he, as I said before, after go to the RALU function, there are a lot of zero, and it really redundant, unexpected redundant. So we can also approach the select how to select a neuron to prune by calculate the non-zero ratio or ratios. Here is, for example, we have three channel and two filter here, and we can calculate the the zero ratios between among their channels, and with the three channel we can see here, um, we can see on the first one on the left have a pi um, pi zero, and is on the right have a 60. So the um, overall the average percentage of zeros is 5.5 plus 6 divided by 2, because we have two channels, two filters, and 4 by 4 is the metric size, and we got the average percentage of 0 here. Similarly with other channel, and with the in this example we will remove the last one because it has highest average percentage of 0. um, we can also select neural to prune by reduce the uh, by minimize the error between the output. We can see here is a really um, here an here is an example uh, with the input matrix X and parameter matrix W, and we multiply it, then we receive the Z matrix. And on the in the below pictures we will choose the vector or some parameter to prune, like like we calculate somehow we calculate um, still inputs x and metric parameter metric is w, but somehow we will prune it to minimize the error between z and z hat. So easy how to choose the neuron to prune, and neural network have a lot of layers, and how to choose the good ratio for each layer to prune we can see here. um, do we need to the different ratio for each layer, or we can choose the same for all layer. The answers is we should choose the different ratio for each layer because in a neural network each layer have a um, different role and it attract different features to generate the output. So one step we need to choose the good pruning ratios is like sensitive analysis for each layer. So how to do this? Let's choose the accuracy when before prunings um, mock here, and for each layer. For example, in this picture, we have a six layer from layer 0 to layer 5, and we choose the pruning ratio from 10 to 90, which step is 10%. So let let's sensitive analysis for each layer. Like for layer 0, we prune 10%, prune um, 20%, 30%, something like that, until 90%. And we repeat it for the layer 1, 2, 3, and 4, and 5. And we have the graph here. It shows the sensitive level and some start when pruning. And with this picture, we can say something. We can find something interesting here, like the most sensitive layers is layer 0 because when this prune about 50%, the accuracy start to decrease, and it's decrease a lot when we increase the pruning rate. Um, in contrast, the layer 1 is less sensitive because until pruning about 70% of neuron is the accuracy start to decrease, and it decreased really slightly. So let's choose a threshold t as a pruning rate that like um, equal that suitable for both um, most objectives when pruning, like it reduce the size of the parameters a lot, and but keep the accuracy in is an acceptance range. But do you think it's a good approach to choose a pruning ratio? Um, any any idea? Do you think it's a good choice for choose the correct pruning ratio? Can you can you share um,
Yes, it
some your
should
idea?
be the model will be lighter, but uh, still having the same accuracy.
Yeah, but do you think this approach is a good way to choose pruning ratio? Are there any other approach? Uh, okay. Um, the answer for these questions is no. you, you can see here we do the process of pruning for each layer. So with this approach we ignore the connection between each layer because in the neural network the the layers interact with others. So with this approach, really a knife approach, um, is ignore the connection between layer. So it's a way when it's a way to sensitive analysis, but I think it's not a good approach for choose the correct pruning ratio. So let's move on to more higher level approach. Um, Here, let's consider the choosing pruning ratios as a reinforcement learning problem. So we have humans as well as the AIs, and we use as a um, reinforcement problem and trainer model to reduce the to minimize the error. The rewards here will equal to minus errors, and we try to minimize this start. But I will not go deeply into this approach, and let's move on to another really um, interesting approach here. Let's see. We have the two objectives when pruning. A, reduce the size of the model. It also means we increase, we reduce the latency, right? And also maintain the accuracy. So let's consider the latencies um, as a metric, um, and um, here, uh, I will introduce you some really amazing approach named NetAdapt. Sorry, because I not mentioned it in the slide, but its name is NetAdapt. So how NetAdapt work? Let's define a latent reduction goals, which mean that the reduce of the latency, but the defined latency reduction goals here is for each layer, and let's call the data R. So for each layer, we prune the this layer until it meets the latency reductions delta R. For example, um, for layer for A, we reduce the size of the we prune the model, and we achieve the accuracy A. Do similar with the other like B, C, D until Z. And for each layer, each for each layer, uh, we after pruning until we reach the latency reduction goal, we have the accuracy, and let's choose the best one. Let's choose the best one, and uh, then short-term fine tuning. The short-term to like recovers a little bit accuracy, and repeat this process for all layer. For example, here we choose the at the first iteration, first step. At the first step, we choose the layer C have the pruning ratio C1, for example, and it have highest accuracy after pruning like ACCC. Then we uh, fine tune it in a short time to recover some accuracy. And the second iteration, let fix this pruning ratio and repeat the same process to other layer. For example, the second iteration, we can find the layer D with ACCD is highest, then we keep it ratio and repeat the short-term fine tuning and repeat this process until we have the we reach the overall latency reduction goal. And then we have the whole model after pruning, then long-term fine tuning to recover the accuracy. So you see um, how NetAdapt work. So is it about how to choose the neuron to pruning, how to choose the pruning ratio. So let's move on to fine tune a prune model. Okay, okay. Um, Feel free to ask me some questions. Yeah, yeah, yeah. It is many iteration. Like um, I cannot draw here, but let's imagine you have like this have four layers, A, B, C, and D, for example, and here here you have a step of repeat process. So I will describe the 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 first three steps here. The first step is like we have a four layer here, four layer neural network here. So yeah, mm, no, it is the same sort. Like we have the original model here, and let's see between C and D. That's C and D. Okay, and for example, let's the layer one and layer two, and when we prune the layer ones to uh, this ratio, we achieve the uh, delta R um, latency and keep all the layer same to the Aussie original model. Let's move on the D, and we prune this layer and to a different ratio in compare with this, and we achieve the the latency reduction goal, and we compare the accuracy, and we can see the accuracy at the C is higher and is the best. So we will keep this pruning ratio for this layer, and then uh, short-term fine tuning this model, this C, this is the C1 after pruning. Okay, so repeat the process here. Is we use this model, we use the C model after pruning to to the 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 second iteration. Like we will choose the C here, like the original model. Yeah, yeah. It's a predefined. For example, um, with the original model, we it take about 1 minute to provide the prediction, and we want to pruning it, and we expect that about 10 seconds. We 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 use the at just about 10 seconds we can receive the prediction. So the overall latency reduction here is 50 seconds, right? So um, delta R here um, is the 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 goal for each layer. For example, we have 10 layers, and the overall reduction goal is 50 seconds. So we can choose something like delta R is 5 seconds for each layer, for example, something like that. But you can approach with other um, other approach for each level, other delta R for each layer. But overall, we can choose the delta R like that. The longer, like the bigger of the data are, the smaller. No, no, no. Delta R is the reduction goal, like the difference between model before tuning and after pruning. The difference, like 1 minute minus 10 second is 50 second. Is the 50 second is reduction goal. No, no. Delta R is the units of delta R is about second, about something related to time. But the tuning ratio, the pruning ratio is about percentage. So here we can see the difference between the ratio, like it is a really small part in compared to the original model, but in the D1, the D model, the pruning ratio may smaller because it keep really many parameters in compared to the original one. Do you understand? Here is we prune more on C, but prune less in D. Okay. Uh, let's move on fine tune a prune model. So here's fine tune a more prune model is really a simple process, but there are some tips and tricks, like we can prune all the model, then thus fine tune um this fine tune one time after pruning, but and it still achieved really high accuracy. But really, but they more higher level approach is iterative pruning and fine tuning. Like after pruning some percent, we fine tune it, then pruning, then fine tunes, and repeat this fine tune and pruning process to achieve higher accuracy and also reduce more the reduce more parameters. So the most effective way is iterative pruning and fine tuning. So that's it. That's my presentation about model pruning, a technique to reduce the size of the model but keep the accuracy is the same, and it can apply to many it have many application on the industries when we want to deploy the model on the edge device, as well as um, we can deploy the LLMs and increase the speed when infer the the LLMs, and we uh, still achieve the acceptance accuracy. So that's it about my presentation. Thanks for listening. Um, okay, okay. It's time for Q&A. Okay. Yeah. Uh, but I do not mention it in the slide, but you can see here. Oh, okay. But it also an application of LM. Can I exit this presentation and search it for you? Okay. Yeah, PyTorch have function to um to do pruning. Yeah. Um. Yes. But I think the most popular ones is channel level pruning because it reduces the oversight of the filter and it support more parallel competition. It still keep parallel competition. Um, um, I don't know about it, but all the image in this presentation is from MIT course, tiny ML, efficient ML course, and it also have lab, and you can try it here. I will send you a link. Um, Here, I will send a miss and send to the um chat box after this meet. Are there any questions? Uh, Actually, I want to to do some demo
Um,
code today, but
okay,
I'm a
I
little
have some questions.
okay.
Is any source that compare model pruning versus quantizations? Like anyone compare that?
Um, I think there's some source, but it is two techniques, and you can combine both of the technique together, and we still achieve that. In the course of MIT efficient LM, the quantization is the lesson after pruning, and after that we can combine pruning as and quantization together to get more and more smaller and speed model. Yeah, yeah. Like remove the um, redundant neurons, redundant parameter, and simply we consider the parameter which are close to the zero or have a small absolute absolute values is more okay have less effective to the prediction. Yeah. Yes, here 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 is uh here's it is fine grain or unstructured pruning, and it's hard to accelerate. So it do not reduce the size. So it it does it do not reduce the size. So it not support to increase the speed. It's in the case of fine grain or unstructured pruning. Yeah. No. It do not, but it is one case of pruning. Right picture? Yeah. Like if we have the structure pruning, like we remove this neuron, let's imagine this fully connected layers, and the and each row is a weight vector, so is a weight matrix, and we remove some rows, so the overall size of the matrix will decrease. No, the in the unstruct unstructured, the matrix size is not changed, but with structure, here is a fully connected example. The the matrix size can reduce like that. Are there any questions? Yeah. No. Let's summary. Here we have inputs like 1, 2, 3, 4, 5, 6, 7, 8, 8 features, and we have uh, some metric here with each column, and we just reduce the rows but keep the column the same, like um, the x1 will still multiply by w1. The x1 is also multiply with w2, but not calculate with w3 and 4, and continue calculate with w5. Yeah, so we cannot reduce, we cannot change the input set. Yeah, the output side. Yeah, the output side of the neurons is, let's see here. So like when we prune some connection, some vector, we receive the output side is just three neuron. But but what we need to take into account here is the output, and the input is not changed, and we just care about the output, right? So for example, the output of this, like, is a really redundant neuron. So the output is also a really redundant neuron, right? Yeah. Yeah. So uh, no, we can see in this image, like in the original one, we have four output in the second layer, but we just have the three output after pruning, right? So it means the neuron here is a really redundant neuron. It may be a redundant neuron. So when we move to the next layer, it is also a matrix here. Um, let's see if we still keep the same one, we just we just ignore this multiply with the removed neuron, right?
Actually, we can see that the input and the output layer is not running, right? So maybe it will not affect the size of input.
Yeah, you can understand like that. The input is still like image, our text, or our data, and the output is also my our class. So we will prune the network, the hidden layer. Are there any questions? So if no question, my presentation will end here. Thanks for listening.